what you'll get is the path of maximum change. That may be important to you because you may not want to take the path of maximum change. You may want to take the path of minimum change, or you may want to go in that direction. So, but you need to know where the maximum change in this field is. And in terms of x, it's just taking the function and taking its derivative with respect to x and y and z. And that's all we've done here. We're just taking those derivatives. In terms of phi, in terms of cylindrical coordinates, you're going to take the first one with respect to rho, but notice what you're going to do with the second one. You're going to take the scalar and take its derivative with respect to phi and then multiply by 1 over rho. Now, as we start to do this, and we start to work with curls and divergences and other formulations, be really careful that you recognize where these 1 over rhos are located. It's not inside here, it's on the outside. Now, because it's on the outside, you cannot cancel out something on the inside with that right there until you've taken the operation. Does that make sense? Richard, I miss you?
Back up just a little bit.
All right. If you've got a 1 over rho, if you have 1 over rho, you cannot cancel that out until you perform this operation here first. In other words, you take the partial with respect to u with respect to phi. Then if you want to cancel a rho out, if there's a rho in there that you can cancel out, then cancel it out. Okay?
I don't see the 1 over rho. I see the rho squared.
Yeah. Well, here's a 1 over rho right here. There's a rho.
The reason you say if there was some in the derivative,
Yeah,
you
just-
take the derivative first and then cancel.
Yeah, the reason I say that, because you can have a function where there's a rho inside and a lot of other things. Don't do any operations with this on the inside until you've first done this, okay? I just wanted to say to do that. That way you won't ever get in trouble. Now sometimes, because it doesn't change with rho, there may be a rho or a rho squared in here, and you could do it and it wouldn't get you in trouble. But I'm just making sure y'all don't get in trouble with it, all right? And then here you have a partial of u with respect to z. Now down here we've got the same thing, but you see this r sign of theta here? It's operating on the derivative, so make sure that you take your derivative and then operate on it. That's what you want to do. So this is just showing you those concepts. And here's another example. You've got a field. It is x squared plus y squared plus xyz. You want to find its directional derivative in the direction of this vector right here. Now, why might you want to find the directional derivative of this in that direction right there at that point? This may be a vector that represents an antenna, some type of an antenna that you're working with. And this may be some function of a scalar field, a voltage field or something that's coming in there. You may want to figure out what proportional part of that is along this direction right here. So what you'll do is, well, I'll show you here. What you'll do is you'll take that gradient of this function first, and then what am I going to do? If I want to find the reflection of a vector on another vector, what do I always do? Dot product. I knew you said dot product. Yeah, I heard you. Yeah. You got it corrected before you said it, didn't you? Yeah, there you go. You dot it. You're going to dot the two together. Okay, so that's all we'll do. We'll take this, substitute in the values of 2 minus 1 and 1 in here, and then we're going to dot the two together. We'll dot that one with this one. So there, this is the evaluation of the vector at that point. Now let's dot the two together. So that's all you do. And what that will do, this is the change of this function in that direction. That's what it is. So you may be interested in that at times. And here's another. We'd like to find the angle at which line x, y, and 2z intersects the ellipsoid x squared plus y squared plus 2z squared. Now that ellipsoid might be the outer housing on an underwater vehicle. I was working with the Navy. We used ellipsoids to define underwater vehicles. We might stretch them out, make them kind of long so they look long and tubular, you know, where the ends are curved. Or we may make them more cylindrical. Sometimes they were spherical. And we've got a line. We want to know the angle between this line, x equal y equal 2z, and this ellipsoid here. Okay, so that's what we're going to be looking for. Now first, we need a vector that represents this. Now, a vector that represents this, every time I have an x, I know it's going to be twice whatever z is, right? Every time there's an x, it's got to be 2 times z. Every y that I have has to be 2 times z. Now, I don't really know what value z is, but if z happen to have a value of lambda, then I know that the vector that will represent this line here, its y component has to be twice this z component, whatever that lambda is, and its x component has to be twice the z component. So I can actually write a vector that represents that line by just substituting in the value here for z, which I'm going to call lambda because I don't really know what it is. And then this would actually represent it. So anywhere along that line, or along that vector, would represent this line. Now, the line and the ellipsoid, where do they meet? Well, what did we say? What we're looking for here is, I know that when they meet, this has to equal to 10, doesn't it? Because it's always got to equal to 10, no matter what, it's got to equal to 10, right? And so what I'm going to do then is, I know at that intersection, then when this thing meets this up here, it's going to have to equal to 10. Now, my value of z is lambda, right? That's what we said it would be. That's my value of z here, lambda. My value of x then is going to have to be 2 lambda. My value of y is going to have to be 2 lambda. So what I'm going to do is I'm going to put 2 lambda in here, square it, plus 2 lambda in here, square it, plus 2 times z, which is just lambda, and I'll square that. So all I'm doing is saying, at the intersection, I don't know what that intersection is, I know that this has to equal 10. And I know that at the intersection, whatever value of lambda or z I choose, this has to be 2 times z and that has to be 2 times z. So we'll just substitute in an unknown lambda. Don't know what it is, but we'll just substitute it in and let's solve for it. So if I put it in here, I'll get a 2 times 2 is 4, 2 times 2 is 4, so that's 8, and here I've got another 2, so that's going to be 9, 10. So on this side, I have a 10 lambda squared is equal to 10. So lambda has to be plus or minus 1, doesn't it? Y'all see what we did? So now this is something you may not remember from your earlier days, or you may have never had it. I don't know. If I gave you a line like this, I said, here's your line, could you write a vector from it? Because here's the way you do it. Okay? You figure out the relationship between one of those terms and the others. And then you use that ratio for the other 2 terms and make a vector out of it, and just let your unknown, because you don't really know what it is, like this one here, we'll just call that lambda. Where lambda could be anything, you could call it z if you really wanted to, but just call it lambda. And you can actually write a vector that represents that line. So now then, taking lambda equal to 1, then my point of intersection is 2 times lambda equal to 1, or 2 here. Okay? It's going to be just lambda equal to 1, so that'll be z. But here that's got to be 2 times that value, and it has to be 2 times the value. So I'm going to get a 2, 2, and a 1, right? Now that's just assuming that we're taking lambda equal plus 1. It could be minus 1. At that point, of course, my vector then becomes, my line vector becomes 2, 2, and 1, right here. Now the surface of this ellipsoid is defined by this function right here. So what do I do next? I want to know, I'm trying to find the intersection where these 2 meet, and I want to know the angle between the 2. So what is something I told you that we're going to use to get an angle? Dot product, but no curls, guys. You can, we could use a curl. But dot product would be the thing we would want to use. So what we'll do is let's find the gradient of this function right here. Because from that I can get its change. So we'll take the gradient of this function right here, which is 2x, ax, 2y, ay, or 2y, ay, and then here we've got 4z, a sub z. A unit vector that is normal to this surface is the gradient divided by its magnitude. That is a normal, okay, normal, perpendicular to that surface at that particular point that we're working at, 2, 2, and 1. So here's a unit vector that is normal to that surface. We have a vector here that's also in the direction of the line. So what do we need to do next? If I want to know the angle between the two, what would I do? Dot product, okay?
Why did you have to calculate the gradient?
Sir?
Why did you have to calculate the gradient again?
Because I'd like to know a normal to this surface, and the
That's
gradient,
The normal component.
it'll give me a normal component to that surface, okay? And so what I'm looking for is, this by definition is the normal to whatever this function is. If this function, whatever its surface is, by definition, if you take its gradient and divide by the magnitude of the gradient, it'll give you a normal component, a little unit vector that's normal to it at that particular point. And so then if I want to know what is the angle between this one and the other, I just dot the two together and divide by the magnitude of the product, of the dot product. And it does turn out that it gives me the sine of this angle phi over here, this thing here. But that just basically gives me my value, which is 74.21 degrees. But it could be plus or minus 2 as well. So you could have, it could be multiple angles there. Because you could go back and put a minus on that and work it the other way as well. Now, if it was a sine, suppose we did work it through and it turned out to be, and we tried to use the sine on this thing, what would the ambiguity be on that one? In other words, we used the curl. I'd have a possible 4 different values for my angle then. Since I've got both a plus or a minus 1 that I'm working with. So it cuts it down. Y'all see how to do that? Now it's not trivial. I mean, you're gonna have to think through some of these things. Hey, y'all have had all the math. I don't really know if in your vector calculus or in your earlier years you actually took a surface or took a line and converted it to a vector. Have y'all done that? You probably did it, but you didn't remember doing it because it's probably not emphasized very much. But as an electrical engineer, people really think that you and I know how to solve math problems. They do. And the reality is, you have solved more math problems than most mathematicians have by the time you finish. I mean, y'all have been through billions of math problems. But they're going to expect you to be smart, guys, to be smarter than they are. And you can do these kind of things. The reason I mentioned it to you is because just because you don't know. Now, when you go get a job, you're not going to know. Somebody's going to ask you something you don't know. So what are y'all going to do? You're not going to call me? No calling? No. No, you're not going to come back. Hey, I got a call Friday from a guy. He said, hey, I'm working on a project. I'm in trouble. Can you help me? I said, no. He doesn't go to school here anymore. No, he's not here. He never went to school here. He was on his work. I said, if I do, I'm going to charge you money. He said, well, I just thought since you were a university, you would just help me out. I said, no, that's the reason they hired you, not me. So guys, you're going to have to, so what are you going to do? When y'all face a problem you don't know what to do, what are you going to do? What's your approach? You're going to do what?
Pull out the calculus book.
You're going to pull out the calculus? Absolutely. That come right, man. Go back to your calculus book. Make sure you hang on to that calculus book. It's one of the few books you need. Okay? Anything that has electrical on it, you need. Anything that has calculus or math on it, you need. Absolutely, it's exactly what you do. Okay? Now, here's what you do not do initially. You do not go jumping on the internet to see if you can find the problem already solved. Because that's a natural tendency. And I'm sure that some of you have gotten into the routine of doing that. If you don't know what to do, you get on the internet, you try to find somebody else that's already solved it for you. Guys, if somebody else has already solved it, they're the ones that they need to be hired to do the job, not you. I don't want y'all doing that. I really don't. Now, you can look at it later after you've already worked on it for a while. Also, the approach is not to take the solution manuals and figure out what the solution manual did, and then you just write down what the solution manual did. If you do that, you're not going to be a good engineer because you're not going to have the confidence to sit down and do it on your own. And once you get engineer attached to your name, people really are going to expect y'all to know what you're doing. Now, you're not. When you first start, you're just not. But y'all know how to do it. That's the point. I mean, Bill, how many problems have you already solved already? 5 or 6? 100,000? I mean, 10,000? How many? Lots of them, haven't you? So I've got to build your confidence now, okay? We've been destroying you for a while. It's time to build you up. Particularly, some of y'all are fixing to step out there next semester. When you finish this course, some of y'all are graduating. And you're going to be stepping out there, and they're going to expect you to know what you're doing. So you can do it, guys. You can do it. Anyway, let's move on.
One more
Yes.
question about the previous slide.
Yes, sir. Yes,
How
sir.
the cosine of rate of theta is equal to the sine of t or whatever?
It just turns out that if you wrote out cosine of theta here, and you looked at those angles, you'd find that this is the reciprocal over here, where this is the angle theta here. This is the equivalent to the sine of that angle right there is all. It's just the equivalent to it.
Are you making an assumption that angle, the way it's drawn, the blue alien, is 90 degrees out? from the
Yeah,
angle
it
line?
is. It is. And that's all. I would just leave it like this and let this be the angle right here. Don't worry about the sine of phi on it. I tell you, it's more confusing than it is helpful. That's just about the angle there. And since we don't care what the sine of phi is anyway, it's not really. Unless, now in this particular case, are they asking, all right, one is normal to, so one is normal to that surface, and we're looking for the angle between those two. I just leave it in theta, because that's the angle you're looking for.
But now they're looking for theta.
If they're equivalent, then they're the same.
Yeah, and let's see, is this one here?
That's what, I'm not seeing which angle, where are you looking at an angle from and to in that drawing?
All right, here's my ace. This is normal to this surface at that particular point. It's actually normal to the surface, okay, at that particular point. And I'm trying to find this angle right here is what I thought, unless what they've done is they flipped around reciprocal to that. No, that's still the sine of this angle right here. I mean, a cosine of that angle right there, which is the angle between those two. Unless there's something else that's adding to it. Find the angle in which the line intersects this
Well,
ellipsoid.
I think they specifically asked for phi.
Oh, did they? Where
Need
did
an
they?
angle phi at the line.
Yeah, that's for the angle
Maybe
between
that's
the
why.
line and the ellipse, so up to the top, which is
Need
phi.
an angle phi.
Oh, I see what you're saying. Yeah, what you're saying is, yeah, we found it between the normal and what we're looking for is the angle between here. That's what you're saying. Yeah, you're right. So that would be equivalent to this, the sine of that angle right there. So it would just be cosine, and then you've got 90 degrees minus that angle right there is what you got to convert it over to that, which would make it essentially the same as the sine of that angle right there. That's what they're saying. Yeah, so what we did is we found the angle between the normal and this, but what we want is between the actual surface and this. And so that's all we've done. But either one of those would, one's equivalent to the other. The cosine of this is equivalent to the sine of that. I guess you can go ahead and solve for that angle there. One's just 90 degrees off from the other, is all. Whether you're looking for the angle between here and here or there, and see the total of those is 90 degrees. So you're right, that's where that phi comes in. One's just 90 off the other. Just subtract it. One's the supplemental, isn't that right? These two angles here are complementary angles. Okay? And so we found this one, but what we really needed was that one, was what we were saying. Because you wanted it off the surface, and this was normal to that surface. This was out perpendicular to it, but what you want is the tangential components, what we're asking for. That's what you're saying, I think. And I believe that's true. But it could be plus or minus. Okay, you could have it on either side. What is flux? Now, we use the word flux a lot. It is not the stuff you use to solder, or in your case, it's not flux that you put on the metal before you weld it. Okay? That's not what we're talking about. Though that is flux. And we use a flux when we're doing soldering. Why do you think you need a flux for soldering? What does flux do, Justin? Do you know? Well, it does, but it does more than that. What does it do? It cleans the surface off so that the electricity, there won't be any roughness there, so the electricity will go through there, or the heat will transfer a lot better. Okay, that's not the flux we're talking about here. Mathematically, flux is no more than just the integral of some vector across a surface. You take a surface, you take some vector, whatever it is, and if you determine how much of that vector goes through the surface, because the vector may be going like this and your surface is here, you know, what proportional part of it goes through that surface? That is called the flux. So in this case, it is some field. E is a field, ds is a surface, and the direction of that ds is always normal to the surface. It's always outward from that surface. So think of flux as an outward flow. You got this field. This field goes through a surface. How much of it actually goes through the surface? That's what you're looking for, okay? Now, why do you think that's important?
You might only want so much leakage of
All right, you may be concerned about leakage, Bill. That's true. You may have a surface here, and guys, if you want the surface to move, you'd sure like your fields to go through that surface, wouldn't you? Because if the fields go through that surface and interact with the charges that are inside that surface, you can make that surface move. And that's, as an engineer, we like moving surfaces. We like doing all kinds of good stuff with this, okay? So you can think of it as analogous to fluid flow. Flux measures the flow of fluid through a surface. If you've got some surface and it leaks, the amount of fluid that flows through that surface is your flux. Does everybody kind of get a feel for that? It's just a field that goes through a surface. So that's all it is, just the amount of that field that passes through that surface. And it passes through normal. You have a surface like that. Here's a normal component, A is the bend. And even though you may have a field that's flowing like that, the only part of this field that will go through that surface right there is the normal component. That little component right there, that little component there. That normal component at that surface is the field, is the stuff that's actually going through. Okay? The rest of it's not. It's following the surface. It doesn't go through it. So that's what we're looking at. Now we're going to look at the divergence of a vector and the divergence theorem. The divergence, we talked about that, remember? It diverges out or it converges in. Goes out, comes in. The divergence of A at any given point is the outward flux. How much of that field is going outward through this surface, this little, but for a divergence, we're going to take the surface and close it. So it's a volume. So rather than just a little surface here that you've got a field going through, we're now talking about a volume that has this whole surface all the way around it. And the question is, how much of this flux goes out of this little volume? And you shrink this little volume down. And if you shrink it down almost to a point, it will tell you what the flow is at that particular, outward flow is at that particular point. That's what it'll do. So here's your divergence. Del dot A is equal to the limit as the volume shrinks down of the surface, the flux going through all this surface. This is a closed surface, okay, you can close the surface. And we start shrinking that volume down to a point, and as we do, how much stuff's going out of that surface? So that's the concept. Now, if you put a charge someplace at a point, you have an electric field that diverges out from that charge. And that electric field is nothing more than a force field that's waiting to find another charge. And if that force field finds another charge, it will move that charge one way or the other. That will have an effect on each other. That's what it'll do. So here's an example. Here's a little point charge or some source here, and flowing out from that point charge are the fields, and they're diverging out from it. Now, interestingly enough, if you were to look at the density of these fields here, the further you get away from that charge, the less dense the fields, right? When you're real close down here, it looks like they're pretty dense here. But when you start getting out here, the effects of those fields are weaker and weaker because they're spherical. When we transmit a frequency from an antenna, when it leaves that antenna, those fields are going out spherical. They're going out in a spherical pattern. By the time they get to you 5 miles away, you can't tell they're spherical anymore. They look like a flat surface coming at you because they don't change much over your antenna or over your body size or anything like that. So these are all diverging out. These are converging in. Here's an example of no convergence. At this point here, whatever comes in goes out. This is a source that is a sink. This is a positive charge that is a negative charge. All right? So if I wanted to find how much stuff's going out of this surface, I have to integrate every part. Like suppose we put a little charge right here on the inside here. I want to figure out what is the flux flowing through the volume, flowing out of the volume of this thing. What's the summation of all the electric fields that are flowing out of the outside of this thing? So I just start integrating. Now when I do, I've got to integrate the flux across the front, the back, the left, the right, the top, and the bottom. So I've got to add up all those effects, because all those effects will be, that's going to tell me what this divergence is as it goes out. I'm sorry? Yeah, they would be the same. Here they would be. Here they would be the same. They'd all be the same as they go out. That's not always true though, I think. Sometimes they don't all go out in a spherical pattern. Sometimes they'll go in one direction because there's another charge sitting over here, and it'll have an effect on it, and it'll bend them. But you're absolutely right. It sure will. All right, so the divergence of A, here's a little closed surface here. It's a volume. Now, here's something I want you to notice. Anytime you have a function that dots with something else, it'll always create what kind of a field? Scalar. Scalar. If you dot two functions together, remember, it creates a scalar field. If you cross two functions together, you'll get a vector field. If you take the divergence of a scalar field, what will you get? You take a scalar field and you take its divergence, it'll tell you the direction of maximum change. What will you get? A vector. Absolutely right. Okay? So now y'all are beginning to see, anytime you see a dot product, that's a scalar. Okay? Now here it is again. Now, please watch me for just a minute, because this is a place you're going to make a mistake if you're like every other class I've ever had. You're going to make a mistake right here. Because what are you going to do? What is the natural tendency? This says take the partial derivative with respect to rho. Rho is your vertical vector out from the z-axis of rho times a sub rho. Now, what is a sub rho? It's the rho component of your vector. Your rho component of your vector, whatever your vector is, the rho component. And you're going to multiply it by rho, and then you're going to take the partial derivative of it. Here's what you're going to do.
Cancel
You're going to
it.
cancel them out. I promise you, at least one of you in here will validate this class by doing that. I would love for none of you to do that. Okay? Do not do that, because and let me show you one thing worse. This one down here. Look at all this stuff here.
R squared.
The natural tendency, and I promise you, somebody will just lop those two off. And you'll come right over here, and you'll see that sign, and that sign, you'll lop it right off there, and you'll get the prettiest little answer you've ever seen, and I'll put a big old 0 on it. Okay? So don't do it. Do not do it. Okay? Does everybody hear me now? Do not do it. Do I need to say it again? Don't do it. Because it is wrong. But it is something that you're just so used to doing it, you'll just fly through it, and you'll nail that thing, and it'll give you the prettiest answer you've ever seen. Worthless. Okay. Now, because these are scalars, you can operate on them. The operation will end up being a scalar. You can easily enough just take the del of A plus the del of B, just like this. And here, what you're doing, you actually have a scalar and a vector. If you have a scalar and a vector, and you have to operate on them. Now, this divergence operator is taking a partial derivative, is what it's doing, with respect to 3 spatial directions. Because of that, if that v varies with the spatial direction, you have to use the chain rule on it. That's all that is. It's just the chain rule. So, Don't just pull that V outside and hold it like this and do the operation, because if you do, it won't work. You'll only have part of your answer. So beware of these type of operations. And then the divergence theorem states that the total outward flux, okay, of a field, here's the total outward flux of a field right here, and the total outward flux means, let's sum up the flux across all this closed surface that goes around this volume, through this closed surface, is the same as the volume integral of the divergence of A. And here's what it's saying. Whatever goes through that surface is changing, is leaving the inside here, is changing. The inside changes by the amount that goes through the surface. Okay? So if you have fields on the inside of this thing and it's changing as it's going through the surface, whatever goes through that surface is no longer on the inside. Would y'all buy that? It's leaving. So how much does it change? It had a certain amount on the inside, and now it's going to be down by a certain amount because that's the amount that's going through the walls. So if you have a source that just keeps on pumping it out, you're in good shape. And we could prove this, but we're not. It's in your book. Besides, y'all don't care anyway. You'll believe me. Okay? I don't want to go back through this because this is not really, to go through this is really not worth the effort. They've got it in the book. Y'all can look at it, but it's not really worth your time. Okay? All right, here's an example, 3.6. We're engineers, so let's apply it. Come on. All right. We want to take the divergence of these vectors. So this one is, these are the same three that we had before, I believe, or maybe similar. Anyway, this one's rectangular, this one's going to be cylindrical, and the last one's spherical. So let's just operate on them. Here they are. You can see that the operation on these are pretty straightforward. You're just going to take the partial of your x term here with respect to x. What do you do with y and z?
They are constant.
They're constants. Same thing here. You're going to take the derivative with respect to y, so you're going to take the derivative of your y term here, that term right there, with respect to y. Now make sure y'all don't mess up on it now. Make sure, because here's what I've seen happen. I've seen students take the derivatives with respect to the whole thing. So you take the derivative here with respect to x, but you do both of those. Don't do that now. Take the x component, y component, z component. Work with them individually. All right? Yes, Jeremy? Yes. He's following. He's there. And this is what you'll end up getting. And here, remember you got your 1 over rho term? Now look, here's that rho term, rho squared right there. Here's your opportunity. Cancel that baby out of there. Okay? Drop it down to a rho. No. Do not do. Okay? So don't do it. And so now here you could do that one, couldn't you? Okay? Because this one is changing only with phi, and you could cancel out the rho because guess where that's going to go anyway? When you take the derivative of that one term there, you take the derivative of this with respect to phi. What is it? 0, because there is no variation in phi there. And of course here you got to vary that one with z. All right? Same thing down here. You can see how ugly these things are. They are ugly. I'm telling you, they're terrible looking. They're easy to manipulate, but they're terrible to do. And you just want to make sure, no. Do not remove that r squared there. Okay? And then you go on through and take it. But you do take the derivative with respect to it. And since it has an r squared down here, now that r squared there can remove that one, can it? Y'all see? This one here can remove that one inside, but you better not mess with that one until you're finished. So you can see, y'all know how to do all those derivatives, but I just wanted to make sure you don't do that, please. I don't know how to write that so that, or encourage you to make sure you remember.
Put it like this.
I will. I promise you, you will have one of those on your test.
Right up at the top.
No, I'm not going to tell you to do it. I'm going to say, okay? No, I'm going to do that. But now, on this particular problem, it turns out that R and rho are the same. This is not in spherical coordinates. This is actually in cylindrical coordinates. I got this from another textbook, one that we used to use. But notice here, if I want to figure out the closed surface integral of d dot ds, okay? Closed surface integral of d dot ds. Notice what I have to do. I'm interested in this closed surface that's inside of this cylinder here, but it's also inside of this one. Here's the surface area here that goes all the way down. Okay, it's just two cylinders, and I want to know the flux that flows through the inside of both of those. Y'all see what I'm saying? Here's a cylinder on the outside. There's a cylinder on the inside. I'm interested in how much flow goes through it. It's like a pipe, and how much water would flow through that pipe. Okay? Yes, sir.
In a test, are you going to ask us to do both ways, or can we pick?
What I may do is I may ask you to validate it. You know, validate one against the other. That way it's easier to just nail both of them. Okay? So don't pick and only pick one. It's like, hey man, I know how to do it. If you ask for a surface interval, if you do a divergence, I'm in trouble. I'm going to ask for both. But I might ask you to do that. I might. And that way you know if you get the right answer, or you know if you don't get the right answer. You just may not know what is the right answer if you get two separate ones. All right, well, let me show you on this one. Now, you got to include every surface on here. All right? You got to include every surface. So you've got an inner surface, an outer surface. The inner surface is this inner surface on the inside of that one right there that goes right down here. So you got an inner surface. You want to know how much flows out of that inner surface because it could flow out and flow up, right? You want to know your outer surface. That's this big one out here. You want to know your bottom and your top. Now, here's the hard part of this. It's not hard, but here's the part of it. You have to figure out what the differential DS's are. That's the first thing you have to do. On the inner surface, inside of this thing right here. Now remember, the normal to that surface is always out of the surface. So which way is out of the surface? Not x-axis, but what it's going. Now remember, rho comes this way, but your surface goes, this little surface area goes the opposite direction. Y'all see that? Because it's always out of the surface. That you're looking for flow out, not flow in. Flow out. Y'all see what I'm saying? You know, you got the one on the inside. And then you got the one on the outside out here. Okay, like that. Now this one on the inside, if it was permeable, stuff could flow through this surface right here, could it not? Couldn't it come back in like that? Right? I mean, anywhere along here, it could flow back out and then flow up or flow down once it gets in there. If that's the outside of that inside surface is in the minus rho direction. Does everybody see that? Got it right? Mm-hmm. All right, good. It's in the minus rho direction. Okay, there it is there. And the surface area will be a rho dz d phi. Why? Because you got to go up in the z direction and you got to go around in the phi direction, and phi is never left by itself. Phi is always r d phi or rho d phi or something to give it a distance. Without it, it's just radians. So this is your inside surface area, and its direction is always out of the flow, or the flow is going to go through it, and it's going to be in the direction the flow would actually go. So it's in the minus a sub rho direction here. So that's what that is. And so when I dot these two together, the only surface for the inside, right here, is in the a sub rho direction, minus a sub rho. And I'm going to dot that with the term r cubed, which is also in the a, this is really rho. So those are the only two components I'm going to have there. And at that location, notice what the radius is. The inner radius is 1 and the outer radius is 2. So r here, which is rho, is equal to 1. That's the reason you see that r equal 1 right there. Because, gang, you're going to have to evaluate it at r equal to 1. Okay? Now, that's another place that I see students make major mistakes. They have a problem. You know, I mean, your class being much more brilliant than normal class will not have this problem. Unless by chance one or two of you slip, but we're going to try to make sure you don't. You have to determine the outward flow direction. In this case, it's flowing outward in the minus rho direction. You also then have to dot that, and then you have to determine what that surface area is. Since the surface area goes up and down in the z direction, it'll be a dz, but you have to sweep it around like this. So what you're doing, you're sweeping around, moving it in the dz direction. When you sweep it around, it is rho d phi, or d theta. D phi, I guess, in this case. So there's that surface. And you evaluate it at r equal to 1. So we've got this one, and we're going to integrate it from z equals 0 to 5, 0 down here to 5 up top, and we're going to integrate it from 0 to 2 pi. So we're going to sweep it all the way around. So there it is. And then we need an outer surface. The outer surface is this one on the outside right here. Okay? It's located, its position is at an r equal to 2. Now this time it's flowing in the rho direction or the r direction in it. That would be the direction that the stuff would flow out of it. And I do the same thing again. I take this function right here, the only one I've got, dot the two together, and integrate it. It's equals 0 to 5 and 0 to 2 pi here. So that gives me my inner and my outer. Now notice I also have a top and a bottom. What direction will it flow here? What direction is that? Z direction, positive Z direction, right? So if it's a positive Z direction, I'm going to vary rho from 1 to 2, and I'm going to sweep phi from 0 to 2 pi. So my little d phi, my little differential change here is r d phi to take care of the sweeping around, and just dr to take care of varying r from 1 to 2. The only problem is when I dot this, okay, and it's going to be in the a sub z direction, when I dot it with something going in the rho or the r direction, what do I get? If you dot something that's going in the rho direction with something that's going in the z direction, and that's the only two components you have, what do you get? 0. No component. Isn't that wonderful? So it goes to 0. And the same thing's true at the bottom. Except the bottom one is now going to be going in the other direction, or you can change your limits here on these two and flip them around. But you're going to get 0 for the top and the bottom, simply because they're going in the z direction, but there's no z component here at all. So the only two components you have are the inner and the outer, and you integrate those out, add them together, and you will get, I don't know what you get, 150 pi. Okay, you get 150 pi. Now, according to our divergence theorem, del dot d dv should give me the same thing. Now what I have to do though is I've got to integrate this del dot d over the volume. Now can you tell me what the volume is? What is the volume? Is it the whole volume of all this stuff in here?
No.
Or is it just the volume right in here?
Yeah,
Yep, it's right in here, okay? So that's what I'm going to do here, okay? I'm going to go from r equal 1 to 2, so that'll take care of my rho direction. I'm going to go phi from 0 to 2 pi. I'm going to go z from 0 to 5. And the change in this will be my r, dr, d phi, dc. That's my little differential voltage, or differential volume. And you can just read that right out of the book. So that's all I'm going to do. And I'm going to multiply it by take my divergence of this term right up here, which will give me a 2r squared. And so there should be, I already had it, is that right, 2r squared? I would have 4. $2 squared. Why don't I have 4, man?
That's the answer from the previous one.
Yeah.
Yeah.
For the back cover. Oh, yeah. Oh, I see what you mean. Yeah. Yeah, they just doubled it. Because what you got is your, wait a minute. Ah, I see. What you're doing is they're actually adding both of those back together. You're adding whatever comes in here and whatever goes out there, you're just adding those two together. That's all you do. They're actually integrating this, Richard, out here. They're doing the outside volume, and they're doing on the inside volume right here. In other words, I don't know why you do that.
I thought we were just doing the volume between the two.
You are. So why do I need to take that and make it full? Something is not right there, from the back cover. From the back cover. Oh, wait. How do I get this as being? Oh,
Partial
yeah,
derivative.
I see what it is. Yeah, I see where I screwed up. Okay? See, what I've got to do, gang, is I have to, this is the actual derivative here. I just took the derivative, okay, of that. That's not what you do. Here's the actual derivative you're going to take in spherical coordinates. That was my problem. See, I just took the derivative. I just said, oh, it's 2r cubed rather than 2r, or I'm sorry, it was actually, 2r, should have been a 3r squared. So that's where I screwed up. But you actually have to go, when it says the back cover, it basically means in the back of your book. If you looked it up, that would be the actual derivative you would take for del dot d if you had that function right there, and it's going to give you a 4 pi r squared. That's what it is. All right? And then once I've got the del dot d and I just put it in here, then I integrate that. So that's where that comes from. I'm not taking the inside versus the outside, which it said back cover. I was thinking, man, that's not right. You're going to integrate it over this volume here, but you have to take the derivative, and you got to do this in cylindrical coordinates. So you're going to have to go into the book or into the text and find out what that derivative, what this del dot is right here. Okay? So that's where that comes from. All right, here's another one. Here's a little solid. This is a little solid conductor or something that has maybe charge on it. And here is the flux right up here. It's going to be in cylindrical coordinates. And we're interested over the range rho equal, let's see, z is going to vary from 0 to 1, and the outside of this thing is rho equal to 1. What's wrong with that? Oh, there it is. So what we want to do is we want to sum up the flux going through all the different surfaces here. So I've got a top and a bottom, and then the outside surface here. That's what we want to do. And so here for, let's see, what is that one? That's going to be my top. Is that what that says? Yeah. Is that what? I can't see it from here. I think it's a T. So the top would be z equal to 1. That's up here. And then the surface that I'm going to integrate here, the little differential area, is going to be, I'm going to change my rho from 0 out here. I'll integrate out here. And then I'm going to sweep my phi around the top of that thing. And so I'll have a rho d phi. Now the rho comes in because that d phi can never be by itself. So I have to have a rho there. And then my d rho just simply means I'm going to sweep it out from 0 out to radius 1. So here's my little differential area here. I'm on my integrals, limits. And so all I'm going to do is take g dot, this component. And the component of that, what direction is this top in? See? It's going in the z direction. So this will be the only component. It'll be a g dot that. An important gang, have to write this as a vector and then take the component of your g that goes in that direction. All right? So here it is here, 10 pi e minus 2. And then for the bottom, I'm going to do the same thing, except this time I'm going to evaluate it if it had a z in it, but the z would be, z is going to be at 0 because I'm down here. And then here's my surface area again, but this time it's going in the minus z direction. You must be able to determine the surface over which the flux is flowing through. There is not a, I can slide through here. By the way, something else, gang, please hear me. If you don't turn in your homework, there is a good chance you will not do well in this course. So, because some of you have not turned in homework, those uploads, I can tell you that can drop your grade as much as 2 grades. I've seen it happen before. Okay? So do not screw around. Get this homework in. Get it done. Make sure y'all do. I just want to encourage you to get it in. It's not optional. You got to get the stuff. You got to do it. I'm going to make you do some MATLAB stuff. I'm going to make you do it because this may be the last exposure you're going to have of this, but not for the rest of y'all who are going to be around for a while. You're going to get much more exposure out of it. But I just mentioned it. Get it in. If you need help, I'll help you. I'm here. But you got to get it. It's not optional. Get it in. Okay. So, and if you have a C, you can end up with an F. If you have an A, Don't come whining to me if you make a C. Unless you just don't care. Right, Justin?
Would be out there, Mama.
Are you sure? So you're not the one I'm talking to?
Right.
There's a number of you who haven't turned it in. I'm not aiming at anyone in particular. I'm just saying, please don't make that mistake. Do not make that mistake. Because it will hurt greatly. Okay? Okay. All right, here's the outside surface. So now we want to integrate around this outside surface out here. So tell me, what is the outside surface area? What direction is it going to go in? Outside surface. Which direction is it going? Row. Okay. Now, if it's going in the row direction, there will not be a row component that you're going to be. It won't be a d row in it. It'll be a dx and a d phi, but you can have a row in it because it's got to be a row d phi and dx. Determine the direction it's going in, and it will not have a dz or d row or d phi component in that direction. In other words, whatever the direction is, if it's dz, it will not have a d. If it's a z direction perpendicular to it, it won't have a dz in it. If it's row, it will not have a d row in it. It will have a row d phi dz. If it's if it was a cut so that it's going around it, it'd be in the phi direction. It will not have a d phi in it. Does that make sense to y'all? If you can kind of get that in your mind, you don't have to worry about this. Y'all can figure it out on your own without having to look at the book. But I really want y'all to get these principles down. So for this case, since it's going in the row direction, coming out here, it has no d row component in here at all. But it will have a dz, and it will have a row d phi because the d phi can't be by itself. It has to have a row. So it's in the a sub row direction, and I'm going to dot it with this term up here. And so the only term that will come out will be the 10 e to the minus 2z row, and it'll be multiplied times this little differential area. Then you're going to evaluate it at what point? What is the, let's see, you're going to integrate. Your limits of integration will be z equals 0 all the way up to 1. Rho will go from 0 out to 1, so it's going to be along there. And then your phi, of course, varies from 0 to 2 pi. Now, since it's down here at, what is the value of z at this point? 0. So if there's a z in it, you put 0. So 0 goes right in there. So that z right there will go to 0. And then, oh, I'm sorry, it's not true, because I'm actually sweeping z, right? It's the row that goes in as a 1. I made a mistake. I was looking at the bottom of this thing. But row actually is going to be the one. It's going to have a value of 1. So there it is right there, row. Then you just add all three of them together, and notice what happens to them. It's 0. Can you tell me what that means? It means there's no divergence. It means, now it doesn't mean there's not a field that goes through it. But what kind of field is it now? There's no divergence, there's no convergence. What does it mean? There's no flux that goes through this. You know why? Because whatever comes in one side goes right out the other side. In other words, it's not originating on the inside. It's flowing through it. Something can flow through it without actually changing while it's on the inside. It's not. It's just going right through it. So you can have a field that's going right through it, but it's not changing as it's going through. In other words, you don't have something on the inside, and as it goes through the outside, it begins to decrease, diminish. It's just the same thing on both sides. So you can actually have that. So if you drew that one, here's what I mean. You have that. But you don't have stuff in here that's flowing out like this. None of that. It's just whatever comes in goes out. Now, I hope by now you're looking at stuff that's been abstract all your life. When you took math, it was abstract. It meant nothing. Now, this has meaning. And it has meaning that can help shape your career as an engineer, and it can help you solve problems. But you're going to have to now add the principles to the math. And we're going to try our very best to help you do that in a way that you'll understand it. So I don't want you looking at this and saying, oh, I don't want to spend my time. No, not want to. Yes, you do want to. Hey, I want you to do it now. I want you to leave You know, when you're playing ball, my coach used to tell me, son, you leave the blood on the practice field, not when you get in the game. Well, I didn't understand what he meant. So the first year I played ball, I was in the sorry shape of anybody on the team. Right? Until about the first end of the first quarter, we were playing football. And the end of the first quarter, my tongue was hanging out on the ground. And I was begging the coach to take me out. And I was, in fact, but someone else took me out before they actually hit me. And I was bigger than they were. I was bigger than they were. I mean, somebody bigger than Armandus over there. I mean, this guy came plowing that. I was big. I was about 235 when I was playing ball. And I was about the size I am now, about the same height. And this little kid come up there and he hit me. And I was just, he took me out. Okay? And I realized and the coach like ran my tail off. He had me out there on Saturday, making me run. Okay? I mean, he sat out there in the stands and watched me run around the track until he got me in shape. Okay? And then I realized what he was talking about. Guys, we're trying to get you in shape right now. And you're going to fight me? That's okay, because I know it'll pay off in the future. But I want y'all to be good. I don't want you to do what I did and get just murdered the first time you get out there on that field. So, anyway, upward and onward. We can apply the divergence theorem, okay? And hopefully we'll get the same answer. So if we do that, here's our gradient of this, and it's an ugly looking little thing here. And basically what we'll show if we took this, if we actually plug in our value for G, which we're going to do, we just put our G in right here, okay? Here's my G rho term, there's my G phi term, there's no G phi term, and there's my G z term right here. And I take those derivatives just like that, and I add them together, guess what I get? I get 0. So when I take this derivative here, it is a plus 20 e to the minus 2z. When I add the two together, they're gone. And so basically it tells me there is no change. There's no flux field sitting on the inside there that's diverging out. There may be some that comes in and flows right through, but there's nothing originating on the inside. This is a neat way. You can actually determine how much charge is on the inside of something by just looking at how much goes through the surface. What the fields are going through the surface. And so we're going to use it, as it says here, often. And again, this is just a definition. The divergence of A at any given point is the outward flux per unit volume as the volume shrinks. So how much of this stuff is flowing out or coming in to this little tiny area? And here it is. It's the closed interval. This means the closed surface around this little area. If I find out how much is going through it, it'll tell me how much is changing or leaving the insides. So that's it. Now we're also going to look at something called Gauss's law. And here D is going to be, this D field is going to be an electric flux density. How about that? This D field is going to create something called an E field because it's a flux density. It's how much of this E field is in a particular cross-sectional area of volume. And if I integrate it over this entire little volume, I'll get this little charge right here. This charge creates that D field, which is diverging away from it. That's what it is. And if I can sum up the effects of all this effect right here, I can determine what that charge is on the inside. Now we're going to work with something called a B field as well. It's going to be the magnetic flux density. So we've got an electric flux density, and that tells me what is the amount of field that flows through a particular area. That's going to be my D here, but it's a density, okay? Flux density. That means per volume, per area, per cross-section, whatever. And this B is going to be a flux density as well, but it's a magnetic flux density. So now we're going to add two more terms to you. We're going to go over them and 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 over them until you get it. But if I take this D field right here, this is an electric flux density, and integrate it over a closed surface that encloses a volume, if I do that, I can tell you what the charge is on the inside. Okay? Now, how much charge is on the inside? Now, I can't tell you individually what the charge, I can only tell you what the total charge on the inside is. Or I can take its divergence here, del dot D, and I can integrate this divergence on the inside, and that'll tell me what's on the inside. These are little charge densities. And that means your body is filled with charge. Do y'all realize that? You're just one big bundle of water and charge. That's all you are. You're about 70-something% water. And you got all these little charges running through your body. You are filled with charge density. Every little blood vessel you got's got all this charge running through it. And then there are the charge that goes from your brain or discharges from your brain. When you give a test, when I give you all a test, your brain discharges, sends all this wonderful information, or short circuits, one of the two. All right, here's the old party example. There's a party going on inside of a house, and the party is the charge. Okay. Now, I know that y'all don't experience this ever, but the noise that's flowing through the outside is the problem, okay? Now, we as engineers don't ever get involved in parties because we're too busy studying. But sometimes we pass parties, and our ears begin to hurt because the noise coming from the house is so loud. Or you drive up to a stop sign, and the guy right next to you has a set of 1,000-watt woofers in his car, and he cranks up his woofers, and the whole car is bouncing off the ground, okay? All right, here's the house, here's the party. The noise is the flux that's going through it, okay? There's no flux coming out of the party if there's no party. But if there's a party, there's noise coming out, right? Same concept. But since y'all would not understand this model, since y'all never have parties and you don't go to parties, it's probably foreign to you since y'all study all the time. I know you do. But that's kind of the concept of it, right? Now, the noise is originating in here. It's not passing from here through. It's originating on the inside. Somebody's got a stereo in there or whatever, and they're running that thing up at 400 or 500 watts, and the window panes on the house are flexing in and out. So that's the concept, right? And of course, here's the other concept. The amount of noise that comes out of that house will tell you about how much partying is going on the inside of the house. And that's the idea of using this divergence theorem and all that we've been talking about. It tells you how much charge, if you can measure how much stuff's going out of this thing, you can figure out how much created it on the inside. Now, that's the idea. For example, because you guys don't understand parties. All right, let's look at Stokes' theorem for just a minute. The curl of a vector, if you take the curl of a vector, which is del cross, if you cross any two vectors, what will you get? A vector. Okay, good. We're going to use Stokes' theorem. All right. Now, here's a contour. Here's a point. Here's a contour here. The curl says it is the axial or the rotational vector whose magnitude is the maximum circulation of this A, whatever it is, as you begin to shrink this thing down. In other words, how much does it rotate? Okay, y'all see these rotations here? It's probably a wire with current going through it. So here's a wire with current going through it, just a straight wire. This is the magnetic field, and I can tell you what direction the current goes in. It's going in that direction. And these are the magnetic fields that go around this wire. So if you have a wire, you have a bunch of little arrows going around your wires. Okay? You know what those little arrows can do? If you put another wire over here, and you have current going in the other direction, it can cause a region between those two where there's no fields whatsoever. It can actually put a force on the two wires to try to separate the wires, to try to move the wires. So here, does that have circulation? Yes. It's rotating. The magnetic field is rotating around. It's going around this thing. And if to take the curl of it, this is del cross A, and it's going to tell me the rotation, and it'll be in the right-hand sense. It's going to give me a vector that's going to be right-handed to that notation there, to that direction. It's called the normal direction to the circulation. And I'm going to take the line integral, closed line integral. Here's my little closed box. We could set it right down here. And if I go around this thing, all the way around it, okay, that will tell me the circulation. And I will represent it with a vector that's going normal to the surface. All right? These things are strange. Yes, they are. And it's not going to immediately pop into your head what I'm talking about. But I think if I can do it enough, if you'll do your homework, if you'll review these examples, then it'll start to make some sense to you. And gang, of all the areas, if you could master a good feel for electromagnetics, they will pay you more money than they will in any other area. But the other side of it is if you just master it, but you don't want to work in it, it will help you decide what kind of problems you have. I don't care if you're going to be a computer engineer. I don't know if you're going to. Okay. Some of y'all are computer engineers or whatever. That's nothing wrong with that. But the biggest problems you have, gang, and in some cases, the problem that you face is that you've got problems with that computer, and it's an electromagnetic interference problem. And it will not work because you're picking up all these other fields, and you don't know why it won't work. And so if you're going to be a computer engineer without electromagnetics, you may as well be a computer scientist. I mean, that's my opinion. Since it's my class, I can have this. Y'all may not agree with it, but I do. I mean, I really believe that way. If you're not going to use the math you have, you may as well be a computer scientist. Y'all realize that we now have a computer science program that requires almost no math? You can do it online. You know what they're going to basically be? They're going to basically be computer technicians. They can install your software is what they're going to do. They can't design anything. A lot of students choose, and it's nothing wrong with computer science. It's okay. It's just that you guys have so darn much math, I hate to see you waste it. Okay? So let's use it. And we're going to give you a real workout in this class on you. All right? So here's the deal on it. I'm going to take A.dl. Okay? I'm going to show you that we're going to go to Stokes' theorem in just a minute. But if I take A.dl, that means take A and dot it with little dl, and the little dl in this particular case is going to go from A to B. So I'm going from here to here. So I'm going along the y-axis, right? So I'm really going, this little dl here is dy. Let me show you how you use the chain rule in applying it to this. Here's your point. This is it's a small area here. This area is real small. It's almost right on P, but it's not. The value of the vector at P is AY, X0, Y0, Z0. This is the Y component because I'm dotting it with dy, A sub Y. So I'm dotting those two together. So that's your Y component of A right here. And then I'm varying it. I'm about 1/2 of dx. So DZ. 1/2 of dz down. From here to here is dz. That's dz, right? But if I go from here to here, that's dz over 2. So by that, you see it over there, Michael? I don't know if I ever block you, man. If I do, I'll get anyway. All right, so there's dz. And so what I want to do is there's my little dz over 2, so that gets me down there, and I want to figure out how much is y changing with respect to z at that point right there. In other words, I'm going to move it down here, and that's nothing more than the chain rule. But it's only in one direction, it's in the y direction. See, I move down here, and I'm going to tell you, I move down this far, it's dz over 2, and now I'm going to see how much does it change in this direction right here. That little how much does this thing change as I'm going down here? Because that's basically what I've got here. This is the chain rule. Okay? If you don't know what it is, I mean, you got your AY here is and this is how far I move down. But all I've done is I'm subtracting from this point right here that amount of stuff because that's how much it changes in the y direction. Real close to it now, not somewhere out in space, but real close to it. I can do that in all directions. I can do it from B to C up here, and now I'm changing dz. So I've got my a sub z component, but I'm going to be varying a sub dy in this case. And I can do it from C to D. In that case, I'm changing, again, I'm doing a minus dy. And then I'm going to do it in my D to A, which is a minus dz. So that's all we've done with this. Now, we're going to add all those together. Add all those together. If we do all those together, guess what's going to drop out of it? If you add all these together, you got this one's a plus, and that's a plus, and that's a minus, and that's a minus. So what's going to drop out? That term right there is going to drop out in. And all we're left with is those partial derivatives. So if we put it back together, and see if I don't know if this is going to say that or not. Yeah, here it is here. So here are those. That's basically those partial derivatives we were just looking at just a minute ago. All the other terms drop out except for this. So we're not going to go through that each time, but that just kind of shows you what you do when you're adding those things. Now here's a vector A, it's equal to minus cosine x, sine y, a sub x. And what we want to do is we want to find the curl of that vector. And these are those equations. We just looked at it, and that's just kind of how they were derived. And so I'm going to take the derivative of each one of those and put it in there. So that's all I do. Just come back here. I'm going to take the z component, which is the z component. There is no z component, so it's 0. But if it was a z component there, I would take its derivative with respect to y. How does it vary with y? But I do have a y component. There it is there. So I'm going to take that y component and figure out how it changes with z. It doesn't change with z, right? So it's 0. So it's gone. And then I'm going to do the same thing here. A sub x is z. A sub x component, how does it change with z? It does not, so it goes to 0. And then an a sub z minus, but there is no a sub z component here, so that one goes to 0. So the first two terms are 0. But then I've got, how does a sub y change with x? So I take a sub y. Does it change with x?
Yes.
Sine x goes to a cosine x, right? So there's my cosine x, cosine y. And then this is a minus a sub x. And how does it change with y? It goes from sine y to cosine y. So there it is right there. So we could rewrite it. And then we could, depending on where we were at different values, you can see what you get here. Just by putting in different values for x and y, this just shows you different values you could get. But you don't have to plug them in until you know exactly what you're looking for, the point you're looking for. So you see how to do that? Did I lose you anywhere, Erica? Sir?
Oh,
Oh,
this is not-
Yeah.
That's what I was.
Okay. So that's the way you do it. And these are just some of the formulations, just to remind you again that you can do the del cross A plus del cross B like this, but here's what you can't do. Your del cross A cross B. What you have to do with that, this is the chain rule again. And this one's a little bit more complicated. You just have to go in there and plug it in there. And this is taking del dot B, so you dot the two, which will create a scalar, and it's going to be multiplied times a vector. The same thing is true here. This is going to take the gradient of A, okay? So you're going to take your A vector and take its gradient here, and then you're going to dot it with B. So you're actually just taking each one of these terms and adding them together. And then down here you see, now what about this? What does that tell you? Does it have circulation? If I gave you some fields and they had things that went around like that, would there be circulation? Would there be a curl? Yes, there would be a curl. What about this one right here? No curl there. What about divergence here? No divergence here. What about divergence here? No divergence there. No divergence whatsoever. Okay, so that's just some basic stuff. Yeah, this is just showing you in Cartesian, spherical, and cylindrical and spherical. All this is in your book. What's important to me is not that you know how to derive it, because I don't care, because nobody's going to make you ever do that. Well, I won't take that back. Some nutball professor probably would sometimes, just to be cruel. But you don't need to do that. I mean, graduate level maybe, undergraduate level no. You need to know how to do it. And what's important is I want to make sure y'all don't screw up any of this stuff by canceling those things out. Right? Just apply. And as you start to do this, you're not going to get the quote answer in the back of the book. You know why? Because a lot of those answers are wrong. They're just plain wrong. I mean, what they did, the guy he keeps changing editions of his book, and he doesn't always change the answers. So even if you get it on, if you can buy the solution manual, and if you get the solution manual, make sure that if you don't agree with the solution manual, you might be right. And I want y'all to have the courage to be right. You know, not to always say, well, if he got it right, he's always right, because he's not. You know what they do? They hire graduate students to work these problems. Could they imagine hiring you to work these problems? No, you're a graduate student. Okay? No, y'all can do it. I'm not putting y'all down. Y'all can do it. There's classes I've had that couldn't, but y'all can. All right, so here's Stokes' theorem. It states that the circulation of a vector field around a closed path L is equal to the surface integral of the curl of A over the open surface. So here's an open surface. Here's the curl here, okay? And we're not going through the proof of this thing. It's very similar. But here is what it says. If you take the closed integral of A dot dl, where dl encloses this surface, see that surface there? If you enclose that surface and take A around the outside of that surface, everywhere around the outside of this surface, it is the same as taking del cross A on the inside of the surface. It's exactly the same. And the reason we love these, Stokes' theorem and divergence theorem, is it makes life so much easier, because sometimes, as you were saying before, it's just a lot easier to do this one maybe than it is to do that one, because that one may really be bad. So you can get the same answer either way. And so that's what it's all about, is getting easy answers. And now to kind of show you how this works, if you, and we talked about this once before, but if I did the curl all the way around here, each one of those, it turns out that I could take the curl of each one of those and over this whole surface area, and I'll get an answer. But I'll get exactly the same answer by just going around the outside and doing the vector dot dl right here. And the reason I will is because that one right there cancels out that one right there, right here. So that one's canceled out, that one's canceled out, that one's canceled out, that one's canceled out. Every one on the inside is canceled out. The only one that will be left is the one around the outside. So you get exactly the same answer. Okay. Here we'll verify Stokes' theorem for the field vector. How are we doing this? Okay. Now here's one. We want to do the closed. We'll do closed surface over the semicircular contour. Then we're going to do the del cross B. All right. So if we do it, we've got L1, then we got this loop, and then we got L3. Here's what's important about it. You've got to make sure that you define DL correctly. When you're going from here to here, what is DL? Let's see what we've got here. Do we have that? All right, this is in spherical coordinates. So as I'm going from here to here, what have I got? I've got my, I'm going to have to dot, here's my, what I'm going to do is I'm going to dot my RDR plus PR dphi plus Z dz. That's my little DL vector, okay? I'm going to dot it with this function up here. And then I'm going to integrate it over each one of these surfaces individually. So you've got to know what this is, and this will be written for you in, this is your R d phi, and it's in the phi direction. This is Z d phi. I thought that thing, wait a minute. Oh, that's all in the R direction. I guess it is. It probably is written in sphere. Well, we can do it since this up here is only in phi. I thought earlier that there was a theta there, but it's not. So that's really in cylindrical coordinates now, because it's R and phi only. It doesn't have a theta component on it. Oh, let me tell you something. And working your homework problems. Do you remember the one that says that where you were converting into spherical coordinates? Remember me telling y'all there were some problems with those MATLAB programs? Remember that? Okay. What they did, and they did it on two different problems, both on, I think it might be problem 2.1 and 2.2, the MATLAB problem 2.1 and 2.2. They fouled up. They got theta and phi filled. All right, they did that. Then, when you write a vector P, you're going to write your R vector, and I don't want to do it. But then I think they do phi and theta. Is that right? Or is it R theta and phi?
That's the way they did it.
It's
but
R
we
theta and
did-
phi.
we-
R theta and phi. It's like this. So what happens is, if you put, but the way they set up some of their problems was the other way. So if you feed these in, flip them around, you get the wrong answer. So make sure that y'all go back and check those. I know you've already handed those in, and I found a bunch of those type problems like that. But when you're going through, just because he's got it in the book does not mean it's right. And what do? What do y'all always do once you get it written? Because most of the time I'm not asking you to write anything hard. I did ask y'all to write the triple vector scalar product and the vector, the scalar triple product and the vector. But that was easy to do. But on these others, what do you always do? Check it with something you know is right. And a lot of those, the problems that they give as examples in there are usually right. Most of those are right. So make sure y'all do that, because I remember I've been going through those the last couple of days on your homework, and I've seen that as a recurring problem. So you dot these two together, and you get your B dot DL. Now we have to decide, where are we going to integrate? Well, we're going to integrate L1. Where's L1? L1 is going to go from R equals 0 to R equals 2, right out here, okay? And let's see, what about my fees don't change because I'm not sweeping it anywhere. If I was, I'd be sweeping it all the way around, but I'm not. So the fee doesn't change, okay? So it's not sweeping. Fee goes from X towards Y. I'm sorry, is that right? Yeah, X towards Y. So I'm not sweeping my fee. My Z doesn't change, so I don't have to worry about that. So that term drops out, and all I'm integrating is R equals 0 to just this one term right here, where the fee is equal to 0 and Z is equal to 0. Then I come up here, and I got to sweep here. Now this time I'm going to sweep fee. And so my R will be constant at 2. Z will be 0. So I'm going to come back here on this next one. And that's what I'm going to do here. I'm going to be sweeping. This is L2. Yeah. R equal to 2 to 2, so that won't change. That's going to be constant. And then I'm going to have this one going from 0 to pi, just half rather than 2 pi. But I'm going to hold I'm going to hold R equal to 2, and I'm going to hold Z equal to 0. And then once I come over here, I'm going to start out here at minus 2 and integrate in. It'll be in the X direction, or in R direction, minus R direction in this case. So that's all I'm doing. R equal to 2 out here, back in that direction there, and I'm going to add them all together. Now, what is it that's going to nail you? Where will you have your problems? Your problems are, if you'll write this out, you don't have any problems. When you come here, the problem is, what is that direction? It's the R direction. What happens to phi? Phi does not change. What happens to z? You always ask those questions. Z does not change. So you put those values in there and just integrate along that one direction. And you do the same thing out here. You hold R constant and Z constant and sweep phi. And then here, you're going to go from R equal to 2 to 0, or minus 2 to 0, or 2 in this particular case. It could be in the minus direction. So that's all we're doing there. Just sweeping it back. And adding all this together. And we can do it the same way by taking the, oh yes, that's one I was looking for. We can do the same thing by taking del cross B. Okay, we can do that, and then we just operate on this function here, just take its curl, and then come here and dot it with ds. And ds is going to be my, let's see, in this particular case, ds is going to be in the z direction. So if it's in the z direction, it will not have a dz component, but it will have an r dr d phi, where r is really right. I just integrated out. I should get the same answer. Okay. So what part of this bothers you, or do you have questions? Do I? Okay. Slide back.
Why was it integrating from 2 and not from -2?
It would normally be a -2, but it's going in the minus row direction dr, so the 2 cancel out, so you just leave them off. Or you could go -2, but if you do, from -2 to 0, you could do that. But if you do, you got to make sure it's going in the minus r direction, row direction, rather than the plus row direction. And all we did is just cancel those 2 items off. It depends. Sometimes you can. I tell you, it depends on how the r varies. You know, what kind of a function of r it is. If it's a function where it's an r or an r cubed or something, an r or an r cubed, it'll always give you trouble if you go negative on it. If it's an r squared, it's okay. It won't matter whether it's plus or minus. So it's whether it's an even or an odd function to answer your question. So you just want to be careful about it. All right, go home.